Yes. Sorry. Just one minute, let me mute this one. Hopefully, it's useful for you. So, Kamen, you can go ahead with your deep explanation and accurate clarification. You can go ahead, Kamen.
All right, thanks, Muhammad. Today, like Muhammad said, we are gonna discuss the second day of the course, which is drilling, fluid, cementing, and casing operations. So the first part, I'm gonna be talking about drilling fluid for 30 minutes, and then 10 minutes questions, and then a break, and then we'll do the same thing for the cementing and casing after the break.
Sorry for interruption, but you will be explaining for the entire duration of meeting for the first and second run.
Yeah, but I agreed with Ahmed, so I don't know, it's up to you, but I'm afraid I cannot cover 56 slides in 30 minutes. If you put...
Yeah, exactly. That's why I told you, you have to explain for the entire duration of meeting. No problem.
Okay.
We'll have another
run. We'll do the same thing as yesterday, as we agreed with Ahmed. So, okay. And then after that, if you want to answer the questions, or Ahmed or someone else wants to answer the questions, they're welcome. So, anyways, what's the drilling fluid? I'm pretty sure you've studied in the fluid mechanics. The fluid, the word of fluid means liquid or gas. So while drilling, we cannot drill ahead any well in the world without having a fluid, i.e. the liquid or gas for drilling. And then, of course, there are several reasons behind this. We are going to be discussing about those functions and reasons of the drilling fluid. So types of drilling fluids, we discussed some of them yesterday: water-based muds, oil-based muds, synthetic muds, air gas mist systems. In Kurdistan, or generally in Iraq, the water-based mud is the most common, because the point of these online courses are to encourage the students about what we are doing in here, because if they get the first choice of being employee, is going to be within Iraq, I'm pretty sure. Okay, so the key drilling fluid issues, we discussed about the functions and the issues of the drilling fluids yesterday. So tonight, the same thing for the first part, will be talking about the drilling fluid functions one by one, and a little bit in more advanced style. Okay, functions of the drilling fluid. Again, we discussed all these points yesterday: the hole cleaning, control of the formation pressure, suspend and release solids, seal permeable formations, minimize formation damage, isolate fluids from formation, maintain wellbore stability, cooling and lubrication, and so on. Okay, so point by point, we are going to be discussing for the first part all these functions of the drilling fluid tonight. Okay, first one. If you see the same slide is repeating like this, just focus on this white one. This is the point we are discussing. So this is the first one, hole cleaning. The drilling fluid helps you to clean the hole by curing the cuttings while drilling. Like we discussed yesterday, of course, when you are drilling ahead any hole, you are either crushing or grinding the cuttings. And where does this cutting go? There must be something to carry and lift it back to surface, and that's done by the drilling fluids. So drilling fluids, in terms of hole cleaning, as the drilling engineer's job and the mud engineer's job, is to focus on the annular velocity. The annular velocity means when we start pumping the mud down the pipe, inside the pipe, it returns back from the annulus and carrying the cuttings back to surface. And there's a critical data in here we need to focus on all the time, is the velocity of this fluid in here. There must be a proper velocity of the fluid to carry most of the cuttings back to surface. If you don't do that, or if you have insufficient fluid velocity, you're going to be dealing with poor hole cleaning, and then probably formation collapsing, and then eventually it can be stuck also. Okay, so as a rule of thumb, the minimum velocity of the fluid in the annulus is 100 feet per minute. So you see in here, that's the minimum. The higher, the better for hole cleaning. Okay, so this is about the hole cleaning. There's one thing that the main thing in terms of hole cleaning is whether you are drilling a vertical hole or a deviated hole or a horizontal hole. The most difficult part of the hole to be cleaned is the deviated hole, and usually above 45 degrees. That's the hardest inclination for hole cleaning. Vertical holes are the easiest for hole cleaning, and then horizontal is second easiest, and then the hardest one, like I said, is between 45 to 65 degrees of inclination. That's the hardest part for hole cleaning. And then we discussed the function of drilling fluids for hole cleaning. Now, second one is the pressure control. Like we discussed also yesterday, when you drill a reservoir, you have a trap pressure, which is called pore pressure or formation pressure. If you don't have an opposite pressure to overcome this pressure, then you are going to be ending up with having influx. It might be a blowout, and that's a catastrophic accident if it happens. So your mud creates a column in the hole, and then that column of the mud generates a hydrostatic pressure, and that hydrostatic pressure must be always more than the formation pressure. And then the formation pressure is either known if you are in the development phase, or if you are in the wildcat well, you can just assume that everything's connected to the seawater, and then you take the water gradient to for your formation pressure calculation. So in this case, your mud must be sufficient and efficient to overcome that trapped pressure or formation pressure, so the kick and well control issue doesn't happen. The calculation for that is pretty simple, and it's been simplified in the oil industry. It's just a conversion factor, which is 0.052 times mud weight in ppg times your vertical depth, not deviated, but vertical depth in feet. Then you can know your hydrostatic pressure. The only thing you can change in that hydrostatic pressure, if you are a certain depth, the depth cannot be changed, obviously. And then the conversion factor is fixed number. The only thing we can change is the mud weight. So that's why it's very important to have a proper mud weight. If for some reason the mud or the hydrostatic pressure is not more than the formation pressure, or it's way more than the formation pressure, then it can cause, if it's less, that means it's called underbalance. It can cause influx. If it's way more, and like I said yesterday, we have at the window how to choose the optimum mud weight. The minimum is your pressure, formation pressure, your hydrostatic pressure, or the mud weight cannot be less than that. If it does, then you're going to end up with kick. And it cannot be more than the formation strength, okay, or the fracture gradient. If it's more, then you are going to break the formation, then you are going to end up with low circulation, or probably washouts, hole instability, or stuck pipe. So that's why it's really important for the well designer, anybody, the drilling engineer who designs the well, the program, he needs to find the optimum mud weight. That mud weight must not be more than the gradient, fracture gradient. That means it should not be more than the formation strength, and it cannot be also less than the formation pressure. This is the calculation I discussed to find the hydrostatic pressure. Okay, suspense cuttings, another function of the drilling fluid is when you are drilling any hole, there are many scenarios, many cases you need to stop pumping. That means you are not pumping any mud into the hole. That means the movement of the fluid in the annulus will be stopped. That means a static condition. In that static condition, your mud And the rheology of your mud, which is called in this case a gel strength, should be sufficient to carry all the cuttings, which is half of the way. You are trying to bring it back to surface, but it's still half of the way or quarter of the way. You stop for connection or for any other cases. You stop pumping. Your must be a proper mud to carry, to suspend all the cuttings within the mud and doesn't fall down. If it does, then you are going to end up with having what they call fill at the bottom of the hole. You always have problem with going in, coming out if you don't do so. We discussed also this point briefly yesterday, minimize the formation damage. If your mud is proper mud, then you can create a proper filter cake. If you have a proper filter cake, then your mud, the damaged materials in your mud cannot penetrate the formation, and then as a result, your reservoir will be uninvaded. If that happens, if you don't have a proper mud and then you damage your formation, for example, if you have way over mud weight, way over than the formation pressure, like I said, you might break the formation, which is called washout. Then if you have washout, that means your hole, for example, it's 8.5 section, and instead of 8.5, your hole can be 14 inch. It can be 12. So that means the hole is getting over gauge. So if it's over gauge, then it's going to be hard to control the directional drilling. And the whole point for drilling any hole is to maintain the directional plan so you can hit the target. If not, the poor zonal isolation. If you have, like I said, over gauge hole, then you set any packer, any isolation equipment, it cannot be set because your hole, instead of 8.5, it can be 12, it can be 14. So that's another issue. Or it can damage your cement, and then poor hole cleaning, and then it can cause also the stuck pipe. And then if you don't have a proper mud while fishing operation, you might fail. All these problems can come from improper mud. So like I said yesterday, the mud is exactly similar to the blood in your body. If you don't have a proper blood, if you have a problem with the blood, that means the entire body doesn't function properly. Yeah, someone ask it? Okay, this is the inhibition for any known well. For example, in HKM, we've drilled several wells before. We know what kind of formation we are drilling and what kind of issues we are facing and we might face. So for that, we add a lot of materials into our mud to what they call inhibition. Inhibition means prevention. For example, we know we have some formation. They are reactive shell. They need a proper inhibition, shell inhibition, so they don't collapse. Minimize formation damage. We discussed this. If you don't have a proper filter cake, or for some reason, if your damaging material in the mud penetrates your formation, it can mess up in your reservoir, and then it's going to be hard, and then probably it impacts on your permeability, on your porosity, and so on. All these are a little bit advanced for mud, so just to save some time, I'm skip because they are necessary for this stage for you guys. And then isolate fluid from the formation. Okay, a part of, if you have, like I said, you have a window. If you have any mud above the window, if it's below the window, you end up with well control. You're going to have a kick. But if it's above the window, above the fracture gradient of the formation, then despite you break the formation, you will also have problem with what they call differential sticking. Differential sticking is one of the sticking mechanism. You have a formation pressure, just for example, is 1,500 PSI. Okay, this is your formation pressure. And then if you multiply by that calculation I showed you guys, if you multiply your mud weight by vertical depth by the conversion factor, for example, you end up with 4,000 PSI. 4,000 PSI is way, way greater than 1,500. So in that case, that 4,000 minus 1,500, so 2,500 psi can push your pipe so hard to the side of the hole, to the slick equipment, slick tools. That means the tool is one size from top to the bottom. That means slick tools. It can adhere to the side of the hole. So instead of your pipe stay in the center of the hole, it goes to one side and adheres there, it sticks there, and you need millions of pounds to make it free. So that's why it's also important to have a proper mud weight. If it's more than the formation strength, then despite the fluid losses, you also have problem with the differential sticking. Another point in here is we discussed this cooling and lubrication. As you know, we have a lot of lubricants, especially we discussed yesterday. One of the systems of the mud is oil-based mud, or even if you have the water-based mud, but if you have some lubricants in your system, in your mud, then it can cool and lubricate your bed first, because the bed, like I said, is the first thing which is crushing or grinding your rock. And the deeper we go down, the harder the rocks become. Especially some rocks like limestone, anhydrite, dolomite, they are so hard. When your bed is crushing it or grinding it, it creates a lot of heat. So the mud can cool and lubricate your bed first. And then also when it comes to the annulus, it can lubricate and cool the other components in your BHA, like your stabilizer, like your directional tools, or if you are in deviated holes, because the casing is like this, and your drill pipe and the entire string also is like this, so it's not vertical, it cannot stay in the center. Of course, your drill pipe is having friction with the casing, so that's another case. Cooling and lubrication of the mud is important. Other consideration, those points I mentioned were major functions of the mud, but there are some other minor, I would say minor, sometimes they are major for our operation as SKN, the major functions of the mud. Power downhole tools, we've got all these downhole tools. We're going to discuss RSS tomorrow. RSS tomorrow is one of the directional tools. MWD, LWD, most of them they have for motor. They have stator and rotor, or they have turbine. So what can create any power in this tool? You don't have electricity, obviously. You don't have any hydraulic in there. So it's the mud. The mud can create the power for those tools. Or the mud creates the pulse when it comes back to surface. Via the pulses of the mud, you can take the readings from the MWD tools, from the LWD tools, from the directional drilling tools. All those tools are sending you data via the pulses of the mud. Another thing is the environment, another consideration. As you know, mud is a damaging material to the environment. If you spill the mud, then you can create and you can spill the environment, more especially in the offshore, because it's a very tiny place to work on. If you, for example, if you spill the oil basement into the sea, that can create issue for the animal lives in the sea. This is as one of the examples. And this is another impact of the environment. Maximum hole information. This is also taken from the uses of mud. We discussed yesterday that the well site geologist is on site just to tell you what formation we are drilling and what kind of lithology. Lithology means whether it's dolomite, anhydrite, shale, clay, whatsoever. How the geology knows this is from the cuttings. He takes the cuttings to the lab and puts in the microscope, and then they describe and they collect the cuttings, and then they can compare, they can correlate to the offset wells. So that's how the geologist on site knows which formation we are drilling. So if you don't have mud or you don't have any drilling fluid, there's nothing to carry all these cuttings back to surface, and you are blind. And for some reason, if you don't have return to surface and you are drilling, they call blind drilling. That means you are blind, you don't know what you are drilling. But if you are lucky, you have a gamma ray and some other LWD tools, you have an idea what formation you are drilling. But the cuttings is the main or the key element to know which formation we are drilling. Another function or use of mud is corrosion. How mud can prevent corrosion is there are some materials they call corrosion inhibitors. You can add, if you suspect, if you predict any corrosion, or if you drill gas wells or high pressure wells, you might expect some corrosion in your mud. So that's why you need to add some corrosion inhibitors. So that's how the mud can inhibit or prevent the corrosion in your system by adding some corrosion inhibitors. So if you don't do that, if you have a lot of corrosion or issues in your mud or downhole, then it can cause the washout. The washout, that means you have a big hole or fracture on your downhole equipment, either the drill pipes or the other BHA components. It can cause a twist of the connection you've made. Any connection on the threads can fall off without having a proper corrosion inhibition. Pumps, mud pumps, because they are all mechanical equipment, they are steel or iron or whatsoever, they can be impacted by corrosion. Another consideration is support part of the DS. The drilling fluid can create a force which is called the buoyancy. The buoyancy means, just like if you swim, when you dive into the swimming pool, you feel that there's a force which pushes you up. That depends on the density of the fluid. It's the same thing when you're running hole with a drill pipe or bit or whatsoever. If there's mud in the hole, there's a force upwards, pushes your equipment back. And that's not a big deal. You never consider a big consideration for the buoyancy factor. And the most importantly is the cost. Of course, if you don't have a proper mud, like I said, the formation can collapse. The cuttings can be a poor cleaning in the borehole, and then eventually you can be stuck and losing millions of dollars. Okay, this is a very, very basic calculation for the well cost, but that doesn't apply worldwide in every kind of operation. It depends on a lot of kind of contracts and daily rates. So it's different how we estimate the daily cost for the drilling rig. So that was about 30 minutes of discussion about the fluid. We have 10 minutes. We can discuss any question.
So, Chairman, thank you for the first part of your informative seminar about drilling fluids, functions, and considerations. So, Jens, whatever question you have, you can ask. We have dedicated this period for questions. Even in Kurdish, do not be shy.
Yeah, I wanted to point out that point. Guys, if you are not confident about your English, or you think your question is very, very beginner's question, don't hesitate. It's all right. It's the best time to ask questions. There is no stupid questions, but there's stupid answers only. So do not be shy to ask any question. Whether in a broken English, it doesn't matter. My first language is not English. I can understand.
So, Kakiman, I'm going to start with a question.
Hello?
Kakiman, I'm going to start with a question. Actually, even in Kurdistan, during drilling, we encounter shale formations, and due to some laboratory experiments, they have published that and discovered we have to saturate the mud with ions. So it's not to change, it's just to prevent the ion exchange between mud and shale formations. So what do you use in HKN for preventing shell swelling, shell collapse, to saturate the mud with ions? Which kind of salt?
Okay. We have been, somebody yesterday asked that question, the challenges we are facing while drilling in HKN blocks. One of them is preventing shell from collapsing. We've had issues in the past and we've been stuck and we've lost millions of dollars because of the shell swelling and collapsing. So we are using KCl as one of the shell inhibitors. KCl is kind of salt. Also, we are using PHPA material, and also we are using what they call DrillTex, IBTex. About 5 agents we have in our system to prevent the shell. The main one is KCl and PHPA. And we have also, like I said, some other material, they have commercial names like DrillTex, IBTex. It depends on the mud company. But we use about 5 agents to prevent the shell, and we have been significantly successful. And my proof for that is, in the past, we used to drill a well in more than a year, but nowadays, Kag Ahmed knows we drilled the well in 45 days, about 4,300 meters.
Thank you, Kak Hemen. Any other question? Any other question, guys?
Hello. Do you have my voice?
Yes,
Thank you so much, Kak Ahmed. Can you tell us about the evaporated formation you faced with HKN, and how do you behave with it for the collapse?
Was the question for me or for Ahmed?
Yes, Kak Hemen, Mr. Abdulsalam.
Okay. Evaporated formation, I don't know what you mean by the evaporated formations.
Like anhydrite.
Okay, anhydrite is the most compatible formation we are drilling. We have no issues with the anhydrite at all. The only issue in anhydrite, which is not a big deal, is we cannot achieve a high ROP while drilling anhydrite. That's the only issue we face.
You have no creep? You have no creep?
No issues in anhydrite. Usually anhydrite is the best formation, and like I said, Kag Ahmed has been with us. We set our casings in the anhydrite. All our casings, we set them in anhydrite. And they are very compatible and very consistent formation. There is no issues other than low ROP because they are naturally very hard rock.
Good. Now, the biggest issue is about the shell formation, yes?
We have, okay, in terms of hole instability is shell, because they collapse, deteriorating the shell on us. On the other hand, we have dolomite and limestone formations, but we have problem with losses, and mainly total losses in those 2 formations, dolomite and limestone. They are on total losses. That means we pump, this is for the beginners, when we pump inside the pipe, the mud, when it comes back to the annulus, there are big vugs and caves and fractures. It cannot come back to surface. So most of the time we drill blindly. That means our mud cannot return to surface because of big fractures in dolomite and limestone.
Yes, thank you. And other question also.
Yes.
Do you have measuring well drilling, logging? I am asking about well logging. Do you have this system, measuring well drilling?
Well logging, measuring well drilling, I'm pretty sure you mean by LWD, logging well drilling.
Logging well drilling or measuring well drilling. Yeah.
MWD, measuring well drilling.
Do you have the system
MWD.
in running?
Yes. MWD, in all systems we have it.
Yes.
MWD is different than LWD. MWD gives you the inclination and the direction of the hole. okay, the azimuth in the inclination. But
Yes.
LWD gives you the log, that means the reservoir or the formation properties. Now,
So-
MWD, we
Yes.
have, if you give me just a second,
Okay.
we drill our wells, especially now the development wells. We have many wells, they are close to each other, right? They are very close. So from beginning, we have MWD tool, impulse tool, so we know which direction we are drilling because it's critical for us. If we hit another hole or another well, it can create issues. So we have MWD right from the beginning. But LWD, logging well drilling, we have it only in the 6-inch hole, the last section, because we produce only in the 6-inch hole, which is our reservoir, and we want to know the characteristics of our reservoir. So we have LWD only in the 6-inch hole. I'm talking about HKM because we are interested only in the 6-inch hole. The rest of the sections, 8.5, 12.25, 17.5, we'll just go ahead drilling without having any information about the reservoir in there. And we might not even have a reservoir.
Thank you so much. I got it. Thank you.
Thank you, Kakeman. Any other question?
Hello, Kakeman.
Hello. Go ahead.
Can you hear me? Can you hear me?
Yeah.
Okay, so my question is about the mud gradient. Yesterday, Kakeman said the mud gradient should be higher than the pore gradient, and also the mud gradient should be less than the fracture gradient. Yeah. So how can we determine the fracture gradient of the reservoir? This is my question.
Kakeman, are there?
I guess he just went out.
Just 1 minute. I'm just. Electricity cut off. Okay, he will be back soon. Kag Ahmed?
Kak Ahmed, what was the question?
I said the mud gradient should be higher than the pore gradient, and also the mud gradient should be less than the fracture gradient. Yeah.
Yeah, exactly.
So how can we determine the fracture gradient of the reservoir?
Before
How
we,
How can we know?
yeah, I got your question.
Yeah.
Before we drill the formation, we have to drill around 3 meters, and then you have to do lick-off test for the formation. And by that way, you can determine the pressure lick-off point, and after that, you will have to calculate the fracture gradient of your formation, depend on your lick-off test.
Okay, I got the answer. Thank you so much.
You're welcome.
Any other question? Mohammed Akram, I think you have a question. He unmuted himself. So, Kak Ahmed, I think let's just end up this meeting because only 2 minutes left for the second round.
Okay, yeah. Let's have 10-minute break and then we come back.
Excuse
okay.
me, before you go,
Yeah, Mr. Absalam,
let
go
me
ahead.
ask a question to Kak Ahmed Rashid, yes?
Yes, yeah.
My question was about measure while drilling or logging while drilling. It's about logging while drilling. How much you trust your data in the moment to make a decision about facing some problems in the reservoir?
You know, about logging while drilling, usually we have to use logging while drilling tools for reservoir section, only for reservoir section, because they are really expensive tools, and we don't have to use it for non-reservoir sections. And for currently, for example, Schlumberger has very development LW tools like microscope. You can even image all your formation through your LWD tools. But even though you have to do wireline logging before you run your completion.
I know how much you trust this data in the moment you are drill and working on the reservoir formation. How trust the data you got it? You know what I mean?
Yeah, I got you. You know, it's not about trusting 100%. It's all about we use logging while drilling tool just to be sure we are in the right way for while drilling. What I mean, to be sure.
Okay, Ahmed.
Yeah.
Sorry for the interruption, but less than 1 minute left, so we shall end up this meeting. And in the third run, you can answer this question.
We can discuss about that one later when we have that.
I'll end it up.
Yeah.
Okay. Thank you so much.
You're welcome.